button. Okay. We hear anything? No one heard anything, but we are recording one way or another. Okay. Recording. I want to go to your site before we get started. All right. So first, under courses, you should see the assignment one. Okay. So assignment one is for unexplained reasons too easy. Okay, it was too easy. I think I drafted the assignment one. When did I send it out? This weekend? Last weekend. Last weekend, yeah. Yeah, it was after a session of snow removal. So I kind of suffered from that kind of a brain freeze. So I just sent it early, and then I realized it was too easy. So apologies for that. I will make sure that next time the assignment will be more difficult. Development environment. Who set up already the development environment? Who? I want to see hands. One person out of the whole class set up the development environment. Two. Okay. All right. Still around 5%. So make sure that when is the assignment due? February 8th, which is next Sunday. Okay. So make sure you don't make sure that you also address this thing over here. I just saw a nickname called the Reaper. Okay, so I don't want to see this type of nicknames in the server. Okay, make sure you are fully identifiable in the server per the instructions. Okay, development environment should be very straightforward. We updated also the repository, the class repository with some kind of a Mac capability. Who was the student who helped me with the Mac? You helped me with the Mac? Docker containers? No? Some other student? You were the student who helped me? Okay, good. All right. Thank you for that. So for those on the Mac, make sure, I think it is another student from another class tried it and it should be working, right?
Yeah, it runs, but because there's no GPU support on the Docker.
There's no GPU support in that specific Docker container. So I was asking, what can we do about it? And it seems that we need to create a new base image of some sort, or
we just run it the regular
locally. No Docker container is not working with GPU acceleration, but locally is working.
Yeah.
Okay. So with just using the UV locally is working. All right. So just for those on the Mac machine, just use it locally with the UV is working fine, and you can get PyTorch to be accelerated locally in your Mac. Okay. So I'm going to put a note in Discord to make sure that everyone is familiar with this, and also add this instruction in the development environment setup so you don't forget. All right. So this assignment gives you some opportunity to review some linear algebra concepts. Okay, so where are you going to find the linear algebra kind of review main concepts that we want you to understand? You have to go to click here, book, all the way to annexes. Okay, I think I provided that link anyway. So start reading a little bit. What is a vector? What is a dot product? Matrix multiplication, dimensionality reduction, things of that nature. This assignment is going to be referred to. We will refer to it in the future when we look at transformer architectures that are doing what is called low rank adaptation, okay, and fine tuning. Okay, when we are dealing with natural language processing. So we'll refer to this assignment. That's why it's there. But this assignment will give you an opportunity to test your development environment, to learn a couple of things about linear algebra, and submit something that matters a bit later on. Okay, that is why the assignment was kind of easy. After that, I think you are done with assignment one, and assignment two is going to show up after you submit it. Okay. again for another 2 weeks. 2 weeks turnaround time. Okay, so let's go back to what we're discussing last week. Okay, so we went through this kind of block diagram, right? Last week. You have to understand what this. What is this S hat? Anyone wants to tell me what is this S hat is? What is this S hat? No one? Yes? The estimated state. Where is it? What state from? This state? Do we attempt to estimate this state or something else? We're never going to be able to estimate this state because this state, we call it a global state, right? We showed you the video with the cars moving around. So that state that the environment is keeping hold of, right, is the global state, the state of what happens 100 cars in front of us, right? We're never going to be able to estimate this state because why? Why will we never be able to estimate the global state here? Because we have limitations in sensing. We estimate something that we can sense, extract information, something that we can sense. If we cannot see what is happening in front of us, 100 cars in front of us, then obviously we cannot estimate the global state. We'll estimate some kind of partially observed, as it's called, state, partially observed, a subset, if you like, of the state, that matters to the task that we are supposed to be doing. What was the task that we were supposed to be doing in this example that I referred to last week? If you go back to your notes, probably you will see it. What was the task we referred to last week? Yes, image classification. Binary classification, in other words, right? So we said, okay, our white hat is going to be right now a number. Is either 0 or 1, right? And the role of this probabilistic reasoning over time then is to do what? For this specific task. Is to change what? Don't be afraid to tell me. I mean, yes. Keep track of what? Of the object. Well, we're not tracking objects here. In fact, we're not localizing objects. We are classifying things. So this guy, this classifier over here is memoryless. It looks at every frame individually. But this guy over here is looking at a sequence of frames. And if this guy, who obviously is a statistical system, it makes mistakes, says that there's no pedestrian in front of you, while the previous frame immediately it was, right? The pedestrian cannot move with the speed of light, right? It has to probably be an incorrect assumption. And so this guy actually keeps a sliding window and corrects for these mistakes, covering the gaps. I also used natural language and another example in natural language to indicate the fact that when I'm writing, you cannot decode every single character that I'm writing, but by looking at all the characters in some sequence, you can infer the characters which are very badly written. Okay. Are we following what's happening? So I should also mention to you that unless something happened, like a snowstorm inside your what is called this room or something like that, there's no excuse of not watching the video and keeping good notes. Okay, because these things will become a little bit like a domino effect after today's lecture, especially, where we'll be introducing some information theoretic concepts and some maximum likelihood concepts. Will be very evident what I'm saying. Okay. All right, so enough with this kind of block diagram. So this was the statistical machine we tried to build. What was this line doing? Why I drew this line? Yes? I cannot hear you. Out of control, this is the machine. Okay? Below the line is the machine. Okay. So in order to learn something, what we need? In order to learn, to build a statistical machine that learns, learns here is be able to predict, yes, what we need. First, we need a hypothesis, but before that, we need the data, the examples, right? That are going to be M of those. And these examples are under the control of something we cannot control, sampler. Another thing what we need, obviously we need someone to evaluate, an evaluator, to evaluate our hypotheses, whether they are okay or not. And someone to say, okay, depending on what evaluator is saying, is to change what? What is this guy is changing?
Weights.
The W's, the parameters. Okay. All right, and finally we are stopping this guy and getting a W star out of which we are able to get a specific hypothesis, which is called final hypothesis, that we will be using to do a prediction for X's we have never seen before. Are we in some good shape? What the task was? Okay. So we went through a linear regression, which was a headline of a specific kind of task, a regression kind of task. What is a regression task? Yes?
Prediction. Best line of prediction.
Line prediction, best line prediction. Well, okay, so definitely we are having a task to understand what is an underlying curve, right? That represents, if you like, this relationship between X and Y. In this case, it was a line per se. But in a bit more practical kind of sense, every time that you see a Y, which is a real number, right? And therefore the label is real number, you're having a regression problem in front of you. Your Y hat will also be real, right? And someone gave you the blue dots and asked you to come up with a good line fitting problem, a good relationship. And what manifests a good relationship in this problem? What is good, this problem? Who is going to tell us? Yeah, the loss function is going to tell us what is happening here without even us knowing the underlying target function that created the data. So we started hitting with multiple hypotheses this problem. We drew the orange line, the green line, whatever, and we arrived with a catalog of 10 hypotheses. And now we looked at a hand-wavy way of introducing a loss function that we call mean square error that will give us back what? What always that loss functions return?
Scalar.
A positive scalar or zero. L is going to be greater than or equal to 0. Okay. And fine, we looked at all these hypotheses. We selected G9 to be the best hypothesis. We had an unfortunate conclusion out of this because we had overfitting. We looked at how to detect overfitting and how to address overfitting via what we call regularization method. Obviously, there are two regularization methods. Well, it's not obvious that there are two, but I'm telling you there are two regularization kind of families. Some regularization methods address the person who was to blame, right, the loss function. Some others address the hypothesis, right? So we'll see both of them in this course, one way or another. Okay. So, this is what? This is where we stopped. Okay, took us 2.5 hours to describe this. Okay, that's fine. So, okay, so since we already covered the LREG, right, the form of the LREG, what is this equation is telling you, this additive thing? When you see loss functions which are additive, what does it tell you? Yes.
You have to minimize this entire expression, so that's why we're adding.
You have to do two things at the same time. You have to do, first of all, what thing is this taking care of? What is the first term is taking care of? No.
First term is a regular mean square error without any regularization.
Yes, but what is it doing? It's taking care of what?
The loss function,
It's taking care of the quality of our predictions. The y hat is there. And the y is there, right? So it's taking care of how close the y should be to the y. The y hat should be close to the y. The second term is always has to do with overfitting. Okay? You have to have good predictions, but not too good. That is the English translation of that LREG. Always write these things down when you review them, because some questions will be like this. Some kind of, obviously this is a too simple question, but some questions will be of this nature, right, in your exams, right, to test your understanding. We're testing intuition here. All right, so who ran the notebook at home this whole past weekend that I was laboring for your assignment one? Yes. Yes, you did it? Okay, how did you do it? How did you run the notebook? No one knows how to run the notebook. Great. That's good. That's great. It's a good starting point in this kind of lecture. So you go to foundations, you go to linear regression, and guess what you do? Have a wild guess. You press the button, okay? You press the button, and then you can run the notebook. Right? That's a breaking observation. Click on this, and then you will be taken to Colab. You press run all, and then all the plots that are associated with this problem will show up. Okay, make sure that you are doing this as you review, because at the same time, while you are looking at the regularization, you have to experience it, right? You have to step through the code, perhaps, to see exactly what W's are getting printed out. Okay. So, bottom line is that we have started with a very simple loss function. Where is this? Okay, here it is. That was the loss function initially, right? The hypothesis minus the y. And then we have lambda over 2 norm squared of w. What we called this norm squared of w? Why we picked it up as a for those who run the notebook, now they know the why. This why question is known. For those who didn't run the notebook, this why question is exactly the same as before. But for those who run it, why we picked it up as an alternative? Did we see some behavior in that notebook that struck us as strange? Yes?
increase the value of high values of weights.
Yes. Because we printed the elements of W with overfitting. We saw some kind of a 400,000, minus 400,000, and things like that there. In its attempt for this thing to go through all the data points, the W's were exhibiting some huge swings. And when we went to the notebook and made this capital M is equal to 3, which is a non-overfitting parameter, right? Complexity, if you like. This capital M captures the highest degree, if you like, of the polynomial that we are hitting as a hypothesis, the loss function with. Then we said that, we saw that the W vector is very well behaving, not a huge swings. The dynamic range is really, really small. And if the dynamic range is huge over here with very large values, this means that 1 over fit, this guy will be, is this guy a vector or a scalar? Huh? Who says a vector? No one. Okay, scalar, it's a scalar. Okay, it's a scalar. Okay, so because we need a scalar, we said that the loss function will evaluate always to positive scalars. So is this a positive scalar? Yes, it is. Therefore, this is a positive scalar. So we are fine in terms of dimensions. We are fine. So this guy will become huge when we overfit. And then what is going to happen? So what? So what if it's becoming huge? What's going to happen? Do we have somebody to change the W? Yes, we do. That's the reason why it's happening. The algorithm, we see back a huge capital L, right? And says, oh, I need to move away from this region of W's that are overfitting. And what region am I going to end up? I will end up in a region where the W star is like this. Why this is good? Why do you think this is good? Another why question. Okay. Why we are here? No, that's not a question, but yes, it could be. Yes.
NVIDIA saves you and sort of takes care of all the near zero values of the weights.
Well, because all the higher terms of the hypothesis are becoming close to zero, what happens to the hypothesis shape? Instead of the blue here, it becomes closer to a nice sinusoidal curve, like closer to capital M is equal to 3. Right? This is why it's good. Okay. Good. So this is the conclusion of our lecture 1. So now let's go to lecture 2 to continue the story. And in this continuation of the story, we are going to go back to, well, hold on a second. Did we present anything about stochastic gradient descent in this class? No. Okay, so before we go to that statistical kind of version of this kind of whole story, I would just want to conclude the discussion with some elementary kind of optimization algorithm, kind of optimization theory based on this kind of iterative algorithms called gradient descent type of algorithms and its cousins. All right, so I'm going to do that and see what happens. Okay. I'm just writing now. Okay, so gradient descent. This is an algorithm that we will study initially. This will be a very bad algorithm. Yes, go ahead.
Sorry, question from the last.
Yes, yes.
We have changed, the number of weights still remains 9.
Yes.
So we have not actually reduced the complexity of our hypothesis set in this case, or we have.
Yeah, it's a good question. And a very nice why question, which I was reserving for the midterm, but unfortunately now I have to respond. Okay, so I'm joking, of course. None of this question will be very simple in the midterm, but I'll give you the answer. Okay, we invested 9 coefficients, right? Think about 9 versus 3 here, you know, like think about it like 9 billion versus 3 billion, because these are the number of parameters that in real life, right, will be dealing. So investing 9 billion parameters while we could iterate with number of models and end up with a 3 billion parameter model, right? Because remember, we went into this kind of discussion to semi-automatically tune the model complexity. That's why we went into this discussion. Otherwise, we could just iterate from capital M is equal to 0, 1, 2, 3, 4, 5, hit overfitting at the 9, go back and see which one is the one that was not overfitting. And I think I showed you a graph where capital M is equal to 3 was the best one. So 3 billion, deploy 3 billion. And that's an approach that will definitely minimize your inference costs, right? Because this is where most of the expenses are on inference costs. Now, what's going to happen here? We're going to deploy a 9 billion parameter model when most of the parameters here are close to 0. And the answer is no. So we will call NVIDIA and say to them, look, we have this problem. And they will send us a tool called TensorRT, who will see a model with a block diagram of some sort, hypothesis, with a lot of zeros, and I'll say, well, I will do it better for you. I will eliminate all these zeros. And I will compress the model down to 3 billion. That's what it's going to happen. And then someone else will say, you know what, I have a better penalty that it will make this become exactly zero. They will be removed anyway from the tool, much more easier than quantization will. Okay. So yes, we are not going to spend 9 billion parameter inference. We will go after the model goes through this kind of tools. They are compressed, and we are fine.
But
Yes.
is it possible that some feature may have a very, very large value so that even if the weight is very small, we can have huge impact on the output?
Okay, so if a feature will have a very if we have, in other words, too many features as we have here, right? And one of these features was too important, the regularizer will not eliminate this feature. In fact, it will have an appreciable weight. It is, in fact, the regularizer will push that weight higher because that feature was important.
What if the value of that feature is very high, let's say 1 lakh, 1 million? So even a small weight can have a huge impact on the total output. So will NVIDIA reject that weight?
Okay, so the tool is looking at, I will go to this kind of discussion. The model compression is not just a weight elimination. It's a different thing. It's not, it evaluates the inference performance to gauge how to compress the model. It's not really blind. It says, oh, let's go ahead and eliminate all the zeros. It does both quantization and model compression. So this will not happen. Now, you can read a little bit more about how these tools are functioning. If I find, there is a very good book, in fact. There's a very good book, in fact, in your O'Reilly library now that you are going to, now that you all have access. Just for the sake of it, let me just bring it up. Come on. What happened? AI Systems Performance Engineering. AI Systems Performance Engineering. That is the book that is going to teach you AI ops. Some elements of AI ops. How to tune these models, which are pretty gigantic, to have to give you a good inference performance at a reduced cost. And many of the quantization stuff are happening, discussions are happening. What I was showing you something about. Oh no, I was just writing this, the great descent. That's what I. Any other questions before we progress? Okay, so I hope you remember from Peter and Carton this function L of W versus W. What is this function? W, where? Let's call that. Let's pretend that this is the function. Right? It's as simple as possible. What we call these functions, convex or concave? Convex. Convex. Concave would be the other way around. Okay? So convex function. This function is the best function that they ever created because it has a very nice global minimum. Okay. So we'll describe the algorithm in this kind of toy example, and then we'll see what is wrong with it. Okay, so you can remember at some point, well, this is the wrong point. Let me draw the line and then tell you about the point. The point here, right? There's a tangent to at that point. Do you remember this ratio from calculus? Let me call this, if I wiggle W, right, by a little, how much of this function will change? That ratio, it has to do with the slope of this tangent function, tangent that I drew. However, this is used to define the derivative of the function with respect to W. In this case, I use the term partial derivatives here. And for those who have a very weak background in calculus, don't panic in the sense that you can always go to that annex. And I told you to review the calculus section from that annex based on Khan Academy question Q&A session on some videos, primitive videos on multivariate calculus. You need multivariate calculus background, but in 30 minutes this is plenty. So this partial derivative of L with respect to W. In the same page, there is a lookup table of partial derivatives that you have to print and have it with you in your exam, because someone may ask you a question about, not specifically, no one is going to ask you about partial derivatives, but you may need to use partial derivative to solve an optimization problem by hand. So what is a partial derivative of W squared with respect to W? 2W. From that lookup table, it's 2W. What happens as the point that I'm considering goes here, and then goes here, and then goes here, and then goes right here in the global minimum?
我去接你吧
What is the slope at that point?
就是说抱抱你，好点见着好点，
The slope is
不要来
0. So in the optimum, right? At optimum, right? The optimal point, the partial derivative of the loss with respect to W is equal to 0. In other words, W star is going to be 0 because 2W star is 0, therefore W star is 0, which is a trivial analytical kind of derivation of what was evident from the plot. So there is some hope, in other words, that an algorithm may start from some random point, like the dot over there, and if it moves in the right direction, which is here on the right, it will find this minimum, and it will stop. That's the behavior we want. This algorithm will be iterative in nature, and it will work with according to this equation. This is a symbol I told you to review from Khan Academy. It's called, anyone? Gradient of the loss, and it's a generalization of the partial derivative. Here we only have a W which is scalar, but when we have a vector, the gradient of the loss is going to be the partial derivative of the loss function with respect to W0. W0 is going to be your first element of W, dot, 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 all the way, partial derivative of the loss with respect to W, capital M, because capital M we denoted the number of parameters from the previous discussion. So in general, W will be a vector like we had it earlier, and effectively this gradient captures some form of direction in this kind of a vector space of M. Where do I go? So the algorithm is kind of very intuitive. It says, imagine you're on top of the mountain and there is fog around you and you want to go down to the valley. Well, one option is to jump into the unknown at the expense of killing yourself, and the other option is to do what? You can see like a foot around you and you can say, okay, this is a step that I can take to go down the most, right? So I'm going to take the step. Here I am, I'm going to look around again, and I'm going to take another step, and so on. So this kind of direction of where you're going is going to be captured by the gradient. And the fact that you're not jumping to the unknown is going to be captured by this guy, which is called the learning rate, and it's typically a small number. very small number. That's all. That's all the gradient descent. It's a descent because it's descending. It finds minima. Okay, so that's good. So we are. So let's see now how it performs. Okay. So to see how it performs, we'll go to your textbook over here, and we implement it in Python. Okay. Your textbook is from chapter 4 of the Zeron's hands-on book. So make sure if I refer to it during the lecture, you don't keep notes here, obviously, because you can't really start writing frantically about this. But you keep a note of what section we have covered, right? Around equation 4.7, right? This is the code that you need to run and your spare time to understand, to step through the code to understand what's happening. Okay. Where are you going to find the code to run it? You're going to find it in the GitHub repository of the author. All right. So we have the equation here. The author is using Greek letters because they would sound a little bit more intelligent, right? So instead of W, we have theta, right? Theta k plus 1 is equal to theta k minus theta gradient of the loss function. We have the same. Do we have a regression problem here? Yes, we do. I didn't show you the data set, but it's similar to what we had earlier. But now we are actually making the discussion even simpler than what we had kind of earlier, because we have 200 points and we are fixing the hypothesis to straight lines only straight line. If we get a straight line hypothesis, we are fixing it. Of course, in reality, we have to find what is the hypothesis, but let's suppose that this is the hypothesis, that we want the gradient descent to find our W's. How many parameters we will have in the hypothesis? If we have a straight line hypothesis, how many parameters we have in the hypothesis? Yes, 2. The question is g of x comma w is equal to w0 plus w1x. We said that many times last week. And the most likely it will also be in your notes, because we drew the hypothesis in that sinusoidal kind of data set. Okay, so the author is finding some kind of a solution by looking at the by magically the W star, as I call it, right? This is involving this equation over here, which is also called the pseudo inverse. Most likely, some of you may have gone through statistics classes. Like, did you hear about least squares before? Least squares, some of you are not in there yet. And obviously, this is the type of solutions that when we see this type of solutions with matrix inversions, what we will do, we will run as fast as possible away from these solutions. Okay, why? Because sooner or later, these solutions will blow up. And because no solution that involves matrix inversions is going to be well behaved. And that's why we are doing other optimization algorithms that are able to find these solutions in a bit more scalable way. The reason why this solution will not work for us is because our data matrices, capital X's, will be huge. It will have millions and millions of rows. So what are you going to do? You're going to pack everything that you have inside a single computer and call it your NumPy pseudo inverse to solve it? No, you're not going to do that. So what we will do instead is we will do exactly what I told you. Where is what I told you? I told you something about this guy. We'll talk about the gradient descent algorithm. So here's the author selects eta, small number I told you, 0.1. Selects a number of iterations to 1,000. How do we know the number of iterations? We don't. Just select a large number, open for the test. And our number of examples that someone gave us is 100, the 100 dots. And where we start? We told you have to select to start the algorithm from a random initial point. What type of random initial point is this? I hope you also review some numerical Python in the first 2 weeks of the course. Very important. You have to review all this kind of stuff if you don't know. Linear algebra, submit your assignment 1, probability, some elementary numerical Python, like the NumPy library here, is always very good to know. Okay, but what is this doing? Anyone who knows NumPy? Yes?
2 cross 1 basically creating a
Sorry, I'll take this guy now and then next time.
it's
Yes.
basically creating a random matrix of 2 rows and 1 column
From which distribution?
from normal distribution.
From normal distribution. Random normal distribution of 2 rows and 1 column. In other words, it creates a random normal vector. What is the size of the normal vector? Obviously 2, because that is the number of parameters we have. Because we need to fit a straight line. Okay. Do we have, if you go back to your notes, you'll see the equation of here. WK plus 1 is equal to WK, and so on. So there's a for loop. No surprises there, but there's a for loop. And then suddenly, boom, we are seeing some kind of nasty things going on here, which is the gradient calculation. So the author selected to do the gradient calculation by lumping together, doing this kind of because the gradient is going to be, since we have 2 parameters, the gradient is going to be of size what? 2. Because the first element of the gradient is going to be the partial derivative of the loss with respect to 1 parameter, W0, and the second element of the gradient with respect to the W1. So 2 elements we see in the gradient vector. So the gradient over here is going to be of size 2. He did that using some kind of a vectorized computation. But luckily for us, we will give you the derivation, by the way, is of this kind of gradients in a non-vectorized form, probably easier to understand, is in the corresponding YouTube video, right, that you know how to get access to, hopefully. And so I derived the 2 elements, one after another, and by hand. Okay, so I advise you to watch that video, right? And understand how we are analytically able to derive the gradient. Obviously, for this simple loss function that we are dealing with here, this is a possibility. But in reality, we cannot analytically derive gradients. We will numerically calculate gradients using specialized libraries, okay, called AutoGrad. We're not really there yet, but so if we have that gradient vector, at the very least, what we can do is we can check the validity of the equation. Do you see, is this equation valid or not? Python implementation. The left-hand side W is equal to the previous W, the right-hand side W, minus eta times the gradients. Is this a vector?
Yes.
Yes. A 2 by 1 vector is equal to another 2 by 1 vector, subtracting from it another 2 by 1 vector after multiplying both elements with 0.1. Hopefully everyone is able to see that. And then finally, after 1,000 iterations, we print the W star. That's your W star. Plotting the hypothesis W0 plus W1x is going to give you that straight line. That data set came from the United Nations data set. The x-axis was the gross domestic product per capita, and the y-axis was the happiness factor of every citizen. Right? So it answers the old question of if money can buy happiness, which obviously it can. Right, so that because the slope is positive. Contrary to various beliefs. All right, so let's see now something more interesting: how the algorithm is operating in each kind of iteration, right? In other words, what we are trying to do here, we're trying to connect two spaces. The first space, this is the parameter space, and the other space is the hypothesis space. How many parameters I have? Two. What are the axes in the parameter space? W, 0, and W, 1. What are the axes in the hypothesis space? Where do I plot the hypothesis? In what axis? X and Y. These are the axes of my hypothesis space. So I'm starting from a random W parameter. I told you, random W parameter. So this is the 0th iteration. That's a starting point. Where am I going next in the parameter space? Where the gradient points to me. Is the gradient a vector? Yes, it is a vector. So the gradient points to me to go there. I'm arriving here. I'm making a small step in the gradient direction. I'm arriving there. So this is what? W1.
Professor,
Yes.
you would not want to go opposite to the gradient. Okay. Would you not want to go opposite to the gradient?
Yeah, whatever the equation is telling me, yes, of course, there's a minus there, right? Because the gradient is pointing to the maximum change, right? We are having a descent, so we have that minus. Right? Okay, so then what we do? We do exactly the same. We are arriving in another point, and so on and so on, dot, dot, dot. And finally, we are hitting our W star. Okay, that's basically what happens. What happens in the hypothesis space? That's your hypothesis for the gray W vector. It could be the least one, it will be vertically, could be vertical, doesn't matter. It's a random line. As the iterations are progressing, and if the data are like this, these are the data, if you remember the data set. In the next iteration, you will actually get something like that. In the next iteration, you will get something like that. And finally, in the final iteration, it will be something like that. And if the loss function is such as it is right now, that has a global minimum, the gradient in this kind of best minimum is going to cause this function to these iterations. In fact, the steps we are making are going to be constantly shrinking in terms of changes in the hypothesis space. You understand the reason? You are approaching the minimum, right? And the gradients are becoming smaller and smaller. The steps are becoming smaller and smaller, the changes. And this is exactly what you see here. Start with a random thing, then you end up with a final hypothesis. If the learning rate is selected, which is called the hyperparameter, similar to the hyperparameter lambda that was earlier in the recognition, I forgot also to mention something about it, but I will mention in the review next time. Okay. You're going to be running out of iteration. In other words, you're going to be running out of you could evolve further, to evolve further, but the step size is too small, it doesn't let you reach the optimal region. And if the learning rate is too large, what's going to happen? You're going to, yes, you're going to overshoot, or you're going to skip the minimum, and good luck with that later on. Okay. So you're not even going to converge anymore. So learning rate tuning is very important in this type of algorithms. And of course, this learning rate and some other hyperparameters we'll mention are correlated quantities. And typically we delegate to specialized tools to select the hyperparameters for us. Now, one standard library that everyone should know is Optuna. And this is a typical hyperparameter optimization library. Obviously, there are hundreds of methods that are implemented, or not hundreds, but definitely tens of methods, from reinforcement learning to Bayesian optimization to whatever have you. And it requires really a complete course almost to go through all these kind of techniques. Yes, go ahead.
We have that. Great.
We have, and we will come to that in a moment. Yes.
If the value of learning rate is very high and we end up overshooting our optimum, won't the value of weight optimize themselves again in the next iteration? Like, won't the line come back down?
We will most likely continue to overshoot, and we may actually diverge. We may go on the other side and diverge from that. And this is actually captured to some degree, if I remember right, captured to some degree over here. So bottom line is that there is obviously this kind of discussion here is for, there's not even a real, in a sense that it's like for almost an academic. We're in a university, so it's academic is good, but these loss functions will not be like this. These are going to be not clockable. This loss function will have very nasty landscapes. And one thing that I wanted to start the discussion about is that is to show you a little bit about the gradient calculation also, because if I go to that section, I think I have the formula over here for gradient calculation. This is the formula for the simple linear hypothesis that we are looking at here. And this is the elements of the gradient we have. We have two elements in the gradient, for W0 and for W1. And look what's going to happen. In order for me to calculate the gradient at a specific iteration, I have to do what? I have to sum over all data points. And it's okay if my data points are 100, 200, 1,000 or whatever. But then if it is like a 200,000 points, that's not realistic algorithm. It's going to be too complex to do just for one iteration, going through all these examples, calculate the gradient. So we have to solve the computational problem. It's a huge computational problem. Why the computational complexity is an issue? Well, because people typically have constraints, and either in terms of time or in terms of compute. Yes, we have to move away from this kind of situation somehow. The other more complicated problem is, as I told you, the loss functions we are going to be dealing with are not going to be as well behaving as we were plotting them just now. The X will be into the billions and billions. And the landscape, obviously you cannot visualize it, but even if you could visualize it, some papers have visualized landscapes down to 3 dimensions. You could see almost what Earth used to be millions of years ago when everything was in flux. You could see some really nasty ridges and all this kind of stuff, right? So you could you have the following kind of behavior. If you do your hand like this and you imagine this to be a kind of a loss function, right, with lots of ridges, right, and and you start from this kind of point over here, the global minimum is right here, as you can see. The global minimum is like right here. You go and you go, boom, you fall into the ridge. Because you only look towards the minimum always, right? You cannot get out. You don't get out. You're stuck on whatever local minimum, as we call it, you found first. So what is a local minimum? Local minimum is because of, this is what the global minimum is. There are two kinds of local minimum. One is a good local minimum. Why this is a good local minimum? Why this one is a good local minimum? Because look at the value of the loss function, almost as the same the value of the loss function at the global minimum. But there are also thousands and thousands of other local minimum. So you could fall into one of these. And what is the worst thing about it is that you don't even know that you have fallen into a bad local minimum or a good local minimum for that matter. So with one stone, two birds situation, we are going to make an important modification to the gradient descent algorithm to allow the algorithm to A, have reduced computational complexity, and B, to escape from local minimum. Okay, let's do that. So the new algorithm we're going to be dealing with is called stochastic gradient descent. And we are going to, instead of us calculating the gradient over m examples, if you remember the equation, there was a summation over m, and calculating, if you like, the gradient of the loss with respect to w. What we will do is we'll split the m examples into MB subsets. These MB subsets called the mini batches. But no one is calling them mini batches, everyone is calling them batches. And for each kind of, what is the size of its mini batch could range from as small as 1 to several thousand. Let me throw a number. Could be even larger. Obviously, the several thousands for for very large kind of data sets, and also for techniques which are even outside of the world of supervised learning or self-supervised learning, where large batch sizes are needed there for another reason which are outside. So what happens now when we are estimating the gradient over a much smaller m number, MB in this kind of case, where the gradient now becomes very noisy. We are trying to find this W star in this, let's say, three-dimensional space. Imagine that the space is completely, there's no light, dark, and you come up with a flashlight here. And at some point, let's say this point is where your W star is, right? And before, you started from somewhere, look somewhere here, and someone is guiding you in a very smooth trajectory and points, finally arrives here in a very smooth trajectory. We'll see a plot in a moment. Right? Well, now that's someone who is holding the flashlight has some form of a Parkinson's problem. Okay. That's basically the behavior. The light goes into some kind of directions and finally finds the W star, but we'll see now what kind of trajectories to make sure that everyone is okay, let's see this trajectory in Python. Okay, so this is now our stochastic gradient descent algorithm. So you can see now there's a new term called an epoch. What is an epoch? From your previous classes, maybe. An epoch is a visitation through the complete data set. We need multiple epochs to converge. Multiple epochs. So instead of having iterations, we have epochs, and we're going through subsets of the data inside this epoch. 50 epochs. Here we see some form of a learning rate schedule that is an unnecessary complication at this moment in time, because everything we have discussed is still valid even for the learning rate to be 0.1. It doesn't have to be changed. But here the author selects to implement some kind of form of scheduling. And what is a learning rate schedule means in practice is that it starts from some kind of a larger learning rate and gradually reduces it as the number of iterations goes towards the minimum. It makes kind of some sense because in the neighborhood where the global minimum is, we want to not overshoot too much. Okay. So nothing changes to the theta. Also, nothing changes to our equation. The equation that you wrote down as wk plus 1 is equal to wk minus theta, etc., is exactly the same. What changes? Two things are changing. First, does the gradient equation as an equation changes? And the answer is no, except from the fact that now we are not calculating the gradient over m, but we're doing the summation over mb. As an equation, nothing changes. But where on earth is the stochastic? You told us about being stochastic in the algorithm. What is the stochasticity about? The stochasticity is coming in because what type of examples are coming in here in every batch are sampled with replacement. What is sampling with replacement? You have an urn, just like in the who watched the sum and product rule probability video? No one. Okay, well, I think the second part of the lecture on the information theory is going to be very fun if you haven't watched that video, because I told you this was the foundational video to watch on probability theory review. And what video I'm referring to? Referring to this video over here. Referring to media, course introduction, probability rules, sum and product rule. I'll mention something about that, but I remember this video and asked the question because I was about to describe the sampling with replacement. I have an urn, a container like I do in this kind of video, and I have inside some kind of widgets. I'm put my hand inside, I'm revealing the identity of the widget, and I'm putting back the widget in. Because I want to do this sampling over and over again. Why I'm putting that widget back in? Because I don't want to change the probability of selecting any of the categories of the widgets that I have inside the there. That's the reason I'm doing it. Otherwise, the whole problem will become even more complicated. All right, so let's go back to that plot over here. So I'm sampling the examples with replacement. Let's assume that my batch size is 8. I'm going to sample with replacement 8 examples out of my data set M, populate my mini batch, calculate the gradient for these 8 examples. Next time that I have to populate another mini batch, I have to do exactly the same thing. And exactly the same thing. So the stochasticity is coming from the fact that the number of examples which are involved in the calculation of the gradient is different every time. I told you about the analogy of this person coming into the room with a flashlight. By the way, I didn't present the Python code first. So this is the Python code I was referring to here. So do you see this random index. This random index picks up one example out of M. Okay. As I told you, the gradient descent, a stochastic gradient descent can have a minimum size of as small as 1. So picks up the example for that corresponding index it's selected and calculates a gradient for it. And also the code is calculating for other minibat sizes. In the hypothesis space, similar things are happening. However, as you can see, the convergence towards the optimal over here, it may not even be monotonic. It is monotonic here, but we may go into the opposite direction where we even temporarily move away from the optimal. Even if we find the optimal, what is happening here? We are oscillating around the W star a lot. That's why you see these lines being right on top of each other with different slopes. So this is a full gradient descent. The smooth thing that we always did, and we told you this is about W because it gets stuck and it's very computationally intensive. Going from a random W to the W star. The author here is using some terminology I'll explain. This is a situation where there is a minibat greater than 1. We are now in the stochastic gradient descent space. And we start from a random W and we are going towards the W star and we are oscillating around it. And when the minibat size is exactly 1, we are doing exactly the same thing and we are oscillating quite a lot. Obviously, these are all plots that are, by definition, plots are for a very, very limited set of parameters and very well-behaving kind of loss functions for this kind of toy examples. One thing is certain. Now we have a minibat size or bat size hyperparameter. We have a learning rate hyperparameter. I have another regularization hyperparameter lambda that I didn't mention, and I will mention next week during the review. And so many of these hyperparameters are starting to accumulate, right? So in reality, what's going to happen? Definitely, you need to have a tool and a lot of experimentation, like an experiment kind of tracking system over there to start using the tool, iterate over many of these values, right? And pick up the best hyperparameters that are available, at least the ones that you saw already, because there could be many others you never seen. Some of the hyperparameters also heavily correlated with each other. That makes the search a little bit more challenging as well. And that's why I suggested to learn to have always available to you a good experiment tracking tool, there are many. One good open source one that I used to use is called ClearML. It's a completely open source Python-based kind of experiment tracking kind of tool. Hugging Face also has tools published which are even more minimal than that. I forgot the name right now. And of course, there is weights and biases, which everybody seems to be using because it's on the web. So weights and biases is like almost a de facto choice, right, for that experiment type. So you can see the plots, and you can make certain choices. In one of your assignments, we will point to one of those tools for experiment tracking. But you're familiar with it out of this course. Okay, any questions on this thing? Any questions? Everything is fine. Great. Okay, so let's now, that's where usually the fun stops and the pain of introducing some probabilities starts. And so I'm going to go back to that kind of Vapnik diagram. And where is it? Over here. And I'm going to start telling you that whatever we have done now, although useful, there cannot be the complete story. Because out of this prediction problem we just solved, the regression problem, square footage, let's say, versus price, you will end up with a price prediction for a house. And guess what? No one is going to be interested about your house prediction. No one is interested about predictions in general, which are absolute. So everyone will be asking, okay, how confident you are about your prediction. This almost by definition changes the framework. You cannot really sort of build predictors, but you have to build the capability inside the predictor to spit out confidence. Yes, your house is $400,000, and I have a confidence of plus or minus $10,000 around that price that I gave you, or I have a confidence of plus or minus $200,000, and these two reports are going to be treated quite differently from your customers, as you can imagine. The same thing for classification. So where is this statistics which is going to come from? Statistical representation of prediction? Well, it's going to come from treating the whole thing in a probabilistic way. And therefore, instead of pretending that there's a data generator that spits out X's, we will now treat X as a sample out of a probability distribution. Okay, so the distribution that I'm going to use is distributions that are produced by deep learning book. So this is P data of X. So I'm going to be suggesting, this is the notation, X filter P data of X. This notation says I'm going to be getting an X as a vector that is a sample out of a multivariate probability distribution, P data. Now, a lot of people are in the business of understanding the structure of these marginal high-dimensional probability distributions. For example, if we are in the business of generating faces of nice people here, right? You can imagine this axis be faces of people, right? And if you knew a lot about this P data of X, you could sample out of it and get other people never existed before. Probably some of you must have some experience with image generation of some sort. That's basically what's happening. But over here, at least right now, we are not, or at least in this class, we're not interested about learning up marginal probability distributions. We're interested about understanding how to solve supervised problems in a probabilistic way. So what we suggest that is still going to have a function f, but we'll take that sample x and produce another random variable now. The y will be a random variable too. Not only x now is a random variable, the y is also a random variable. So the y, if someone asks you to describe the distribution, that the y can be described, what would be that distribution? The data of y given x.
Conditional.
Because it's conditional. Because x now is given. What is the meaning of a conditional probability distribution? After the given symbol, everything quoted stops being a random variable. You have now a specific value of x. An image was generated out of a probability distribution, sampled out of a probability distribution. Given that image, can you tell me whether there is a pedestrian or not? Therefore, the y is going to now be a number between 0 and 1. So if I tell you, yeah, you know, I think there is a pedestrian with y being 0.95, what would you interpret that prediction? You are 95% certain that there is a pedestrian. But there's also a 5% chance it isn't. There isn't anyone. Okay. Same situation will happen with regression, as we'll see. Now, this is the point where I ask you to whether you studied your two axioms of probability, which is the sum rule and the product rule. So let's review a little bit the sum rule and the product rule. Open a parenthesis. Sum rule. As you can see in the video, I'm deriving the sum rule and product rule for the simplest possible problem ever, which is a binary, random variables, and two random variables only. So I have two random variables, x and y. Both of them are going to be binary. And I'm asking you some questions about conditional information. If I give you some information about marginal information, for example. It's actually very common in machine learning, AI, and so on. So I will present the sum rule now, which goes as follows. If someone gives you something about a joint and asks you something about the marginal, the sum rule is applicable. This operation is called marginalization operation. You get rid of the y by summing over all possible values of y to obtain the p of x. That's an axiom. The same thing, of course, you can write it as p of y is equal to summation over x of p of x comma y. Whatever information you want to keep, you use this marginalization operation. We'll see that in a moment how it is used in our setting. Okay, so what is the product rule? We're facing a pretty complicated joint probability distribution. And we're interested to see whether by factorizing it, writing in other words as a product, can lead to a simpler estimation problem. As we'll see, the whole space of AI is an estimator. We'll see now the probability distribution. If we estimate a specific probability distribution, we are solving all statistical AI problems in existence, which is quite a lot today, like 99%. So these are the two actions introduced in that kind of video. Please go ahead and watch the video. Typically, students subscribe to my videos in the beginning of the class and unsubscribe immediately afterwards. So do the same. It's okay. It's okay to unsubscribe. Okay. So now we introduce this kind of two actions. I have the feeling that some of you may want to have a little bit of a practical setting of how to experience this joint and conditional probability distribution instead of being kind of abstract formula. So I'll give you an example from real life. Supposedly in every room here there is a thermostat of some sort. Apparently they have run out of thermostat because of the cold. Yeah, maybe this is a thermostat. Everyone knows the thermostat what it's doing, right? It is estimating the indoor kind of temperature. And let's assume that like every device, the temperature over here, which I'll call X, obviously the temperature is a random variable. It would be random, it would also be affected by physics, by nature. So if I am to, it's a continuous random variable, obviously it's a continuous random variable, and therefore I will select the simplest possible probability distribution, right? That it is a Gaussian probability distribution to represent this random variable. So the temperature that you see on the thermostat is one value, right? It cannot be many, you don't see many temperatures, right? Despite the fact that the sensor that senses the temperature has this behavior. It reports some kind of it has the following kind of behavior. Say X is distributed according to a normal distribution with let me write it in two steps. X is equal to X true plus epsilon. But epsilon is normal with zero mean and some standard deviation. This is what you read. This one you cannot know. This is the true temperature in the room. If you bring an instrument from Switzerland to measure the temperature, that's probably very close to X2. But the epsilon over here is some kind of an error. At every vendor of thermostats has its own epsilon distribution. I'm guessing for me, I'm betting on the fact that the epsilon for me is normal with zero mean sigma squared. Someone called me just now. Where's my phone? I didn't put do not disturb this thing. Oh. I got someone told me I've forgotten my phone here. Okay. What I was saying? I was saying something about the temperature, right? So I was saying that why we have zero mean here? Why zero mean is a good model? In other words, what we are saying by having a zero mean as an epsilon. This sensor that we have bought doesn't have systematic errors. That's what we say. In other words, if the mean was not zero and it was 2, always the sensor will actually report 2 degrees more than what the reality is, right? And in fact, it may already do. Some of them do. But let's assume that it's zero mean, doesn't introduce systematic errors, but it doesn't have perfect measurements, right? Perfect sensing, right? It has some standard deviation around the mean. And the mean is what? That's the question for you. What is the mean? So I can drink some water. What is the mean? What is the expected value of X? Yes? Yeah, we can see the mean here, great. But here, what is the mean? Equation-wise, it is X true. If I add a normal Gaussian random variable to something which is constant, right? What am I doing? The random variable has zero mean. So I'm adding something which is constant. So it's like a straight line and you're adding a noise on top of it, right? The mean of that is equivalent as if having exactly the same thing. As having X being now normal with X true, comma sigma squared. The proper distribution is telling us story. It's telling us that the temperatures you're going to see this kind of sensor are going to be many of them around the mean or small number of them around the mean. Many of the temperatures you read on the display are going to be around the mean. That is the nature of your Gaussian distribution, and far less number of them will be far away from the mean. That is the story that every distribution is telling us. So that is the indoor temperature story. Now let's assume that I have another sensor outside of the wall over there. There is no HVAC system operating, as is of course true today. Let me call X to be X in. And I'll do another plot with over here. This is going to be my X out. The same behavior of the sensor is going to be there. There will be some X throughout. X out is going to be normal with X through out, comma, sigma squared. In fact, the two sigmas will be different too. Doesn't really matter. Do you understand what's happening? I'm going to be reading also outdoor temperatures. And the question I have for you is, if I now jointly see to describe the probabilistic nature of the two sensors, have two random variables, X in and X out, right? What probability distribution am I using to describe them? What we call this probability distribution?
Gaussian.
Joint or multivariate Gaussian. I have a two-variate Gaussian or bivariate Gaussian. That's what you will see in statistics books. That you will also see in the Ian Goodfellow's book. And you may wonder why we are so concerned with Gaussians. We are concerned because many problems, the Gaussians are everywhere in nature. Right now, if it was a much larger room, when I was speaking, sound waves arriving in your sensors, and when they are arriving via many reflections, the summation of these waves end up being a Gaussian distribution. The same thing happens with your smartphones as we speak. Lots of stuff in nature, when they are summed up together, independently of their origin, they end up being Gaussians. Heights of women are Gaussians. Heights of men are Gaussians. Over a population. So lots of stuff in nature in Gaussians. Gaussians are everything. Okay, so I asked you about the joint. P X1 in, comma, X out. If we are to plot in what we call a scatter plot, let's call X out here. I have an underlying joint probability distribution, which is bivariate Gaussian. And I'm asking you now to tell me what you expect to see if I read both sensors at the same time. What kind of plot do you expect to see? First of all, we are drawing samples, so there will be points. I'm claiming that you will get a cloud of points like this. And this cloud of points tells us another story. In the absence of any HVAC control, any air conditioning, in other words, right? The higher the outdoor temperature becomes, what happens to the indoor temperature? Goes up or down? Up. So the indoor and outdoor temperature are, we call it statistically, positive or negative correlated. Positive correlated. So in fact, this concept of capturing correlations between random variables is of great essence in everything we do. We see it in dimensionality reduction, because in many problems, not in all problems that we are dealing with, data live in a reduced dimensional space called manifold. And these manifolds, if we describe well this kind of manifolds, we capture the essence of the neighborhood of the data. That's kind of great ways of capturing statistical properties of this data and actually learning easier building statistical machines, which are also quite efficient. So there's another set of plots called contour plots. And you see plots like this. Because the underlying Gaussian probability distribution joined by varied Gaussian probability distribution is going to be represented by a contour plot. What every line kind of designates here is equal likelihood. And so you can see this kind of trend where the higher the outdoor temperature becomes, the higher the indoor temperature becomes. And if we have HVAC here operating, right? With the higher the outdoor temperature becomes, with HVAC operating, then the HVAC will have to work harder, right? The indoor temperature will remain kind of constant, right? We're attempting to create kind of constant, to have a constant kind of temperature. But in general, you can see negative correlations. In general, how the negative correlation will look like. You understand what I'm plotting over here? It's part of your probability review that I asked you to do. The larger the X out becomes, the smaller the input, the X input becomes, negative correlated. And of course, there are uncorrelated random variables where we don't have any correlation. For example, the price of the stock, Tesla stock, and the weather. Okay, two uncorrelated random variables. We'll refer to it in a moment, by the way, when we introduce likelihood and the specific, we call it independent random variables also because something good about that, the independence. We can use the independence to factorize things that we are interested in. Yeah, so I hope if someone is asking you about the conditional that we said about the product rule, what will be the conditional if someone tells you, you know what, tell me something about the input temperature if the outdoor temperature is fixed to minus 20 Fahrenheit. So what is this notion? P X in given X out is equal minus 20. That is a notion. That is the probabilistic thing that we're interested in. We're interested in find something about a random variable if given another one. Tell me something about y if the X is something, is this image. Same thing. And as you can see here, if the joint is like this, and someone fixes for us the X out, the X in will be a univariate Gaussian. There's only one random variable. As it turns out, this is also Gaussian. The conditional is also Gaussian. But we look like this. So we can statistically sample the X in out of the condition. And say, okay, I have a reading for you. And there are formulas in your math for machine learning book, which is linked in your site, which is how probability review, that has this explicit formulas for giving you the statistics of a conditional Gaussian. But these formulas are not concerned to us right now, at least. All we need to understand is what is the notion of a conditional? Something is given to us, some joint information is present, and we can determine something about other random variables involved in the joint. And as we'll see, using the sum rule and the product rule, we are able to see this conditionals and marginals coming together. The product to define the joint. And let's see how this product rule shows up in the Vapnik block diagram. I told you that this is your x, this is your y. Do you see now how they come into the Vapnik diagram? The sampler is giving you jointly x and y. So how do I describe probabilistically what the sampler is giving me as the output? If someone answers this question, I'm going to reward them 0.01 points. Come on. I'm writing P data of x comma y. Because someone jointly give me x and y at the same time. But if I apply the product rule, what should I get?
Data of y given x times p of x.
Do you see the product rule now? Okay. Now, in the notation-wise, because we are given a finite number of examples, someone is giving us information about the empirical, as we call it, probability distribution. So that's why in many textbooks you will see a hat on top of it. That's basically the meaning. All right, so fine. Anything which is outside of control, someone's giving us this information that we can sample examples from. Before, what we are trying to do is to approximate the function f using yet another function. Now, which probability distribution you think we need to understand with our hypothesis? Which of the three? Which of the three? I have three orange probability distributions. Tell us which one.
P data x y. The bivariate.
Would be able to generate predictions. So when the model is determined, right, which one the model should be able to capture? This guy over here. I want to have a P model of y given x comma w. I want the hypothesis to be a P model, probabilistic model, a statistical model that is going to be a conditional statistical model. I'm going to give it an x, and for a certain set of parameters w, it will give me statistical information about the y. And this is going to end up being sampling what? The y. This was my prediction. That is an LLM, that is a VLM, that is a VLA, that's whatever overcomplicated term you can consider, right? This is basically it. A simple linear regression, a classifier, whatever. That's a whole domain of AI today. How to estimate the parameters of a P model. But before, since we are getting the y hat out of function, and now the y hat is going to be obtained as sampling out of a probability distribution, we wanted the y hat to be close to the y, right? That's what we told you. We invented a loss function to give you a function of that difference of the y hat and the y. Now what we need to give you? We need to give you a function. Still will return a scalar back to you, but this function will capture the difference between two probability distributions. One that we are trying to model to estimate the W so that the P model is close to this guy over here. So these two will need to come together. We are now in the business of estimating a probability distribution that will be as close to a probability distribution that generated our labels. That is the English translation. Therefore, we cannot have a function here where we will have a function, but this function will be not y hat and y, it will be a function that will allow a metric to be computed between a distance between two probability distributions. The P model and the P data. And after this emotional discovery, what we are going to do now is we are going to define this thing. We need a new loss function. At the end of the day, meaning probably in the next lecture, this function will be called cross entropy. But we need to derive it. We need to understand why it came, why it makes sense even. A lot of why questions to be answered to make sure that we understand, can answer these questions if someone asks us. And also we understand when we type in the PyTorch binary cross entropy, whatever, what is behind it? Yes.
By taking the difference, we get like the univariate noise, right?
The difference
Of P.
Oh,
P data.
definitely we cannot model everything. Just like before, we could not model all possible variability. We will not be able to model everything. In fact, it doesn't even make sense to model everything. Because if we attempt to model everything, we may overfit, just like earlier. Overfitting will stay with us. All right, so let's now work towards the headline here is basics of info theory. And I want to start with a question. The question is, finally, after this successful course, you are hired as a hedge fund manager. And finally, you made it. And you know, these guys are in the business of acquiring information in a legal way. And two people come to you, says, you know what, I have a piece of information from you, but I want you to give me money to reveal. And an envelope is handed in, and it says that Monday morning at 8:00 a.m. an inbound lanes into Manhattan from New Jersey. There will be no cash, absolutely nothing. No holiday though, nothing, just normal or working day. Another guy comes along and says, the inbound lanes to Manhattan on Monday morning at 8 a.m. is going to be a parking lot. Like complete congestion. As a hedge fund manager, which one of the two envelopes you will be willing to pay money to acquire? Anyone who is empty of any car. Anyone who is full of cars, parking lot, as we call it. Okay, you have to vote either one or two. So sitting there says, okay, let's wait and see what's going to happen. Does not cut it. Let's see. Option one. No one is voting for option one.
Be trying to just provide information to see whether it's going to be empty at 8 a.m.
No, not both. It would either or.
Yeah.
Either I'm going to pay this guy or the other guy.
Like, if I already assume it's going to be full at 8 a.m., so
Full of cars. Okay, who is voting for full of cars? That's one. Who believes that full of cars is the most reasonable answer?
Oh, yeah.
Who? Okay. How about empty of any vehicle. Okay, the other people do not vote. Okay, that's fine. All right. So many decades ago, there was a guy called Claude Shannon. This is the reason why the infamous, famous coding agent is called Claude as well. That invented information theory and actually provided an answer to the problem here. And basically, he said the following intuitive answer: why are you willing to give money to acquire information that everyone accepts as true? In fact, what you want to do is to pay money to acquire information which causes you the most surprise. That is the argument. He provided a formula called value of information, which is denoted here by capital I. And the formula is going to define some interesting quantities for us. It is in fact a log of 1 over p of that random event. Right? So the more unlikely an random event can be, the higher the value it commands. To tell you a little bit more about it, let's look at the following experiment. We have a document that we are stripping out all possible characters except from the English lowercase characters and the space symbol. That's 27 characters. And we are running the experiment as follows. For every character we meet, we increment a counter. We reach the end of the document, we divide by the total number of characters we have seen, and estimate the probability of this random. And over here, we go back to the formula, the Shannon value of information, and we calculate the value. The value comes with a very interesting quantity. The unit of that value is bits. That's where the term bit was generated. But so you can see here the value of J, which turns out to be the least possible symbol, the most unlikely event that can be generated, that can be made in this specific experiment, has 10.7 bits as compared to the space symbol over here, which is denoted by dash, which is very likely and commands 2.4 bits. And entropy, which is the second kind of quantity that we'd like to learn something about, is yet another quantity which is also given in bits, but it represents an expectation. In other words, entropy is the number of bits which I'm willing to pay to acquire events out of the probability distribution of that activity. Is it a discrete probability distribution? Yes, it is. It is 27 discrete events that potentially happen. So what I'm going to do is every event commands this value, right? This is a formula for value of information. And it's weighted by the probability of meeting that event, PR. So as you can see here is an expectation, an average quantity. So on average, I'm going to be paying 4.1 bits to be able to receive events out of that distribution. Now the entropy comes very frequently in as a concept in on our attempt to define that statistical version of the loss function called mean square error in the regression problem we saw. And also in classification problems, we haven't seen any classification problem yet, at least analytically. And instead of 27 sort of possible events, I think it's instructive to see what happens when we have just 2 events. And in fact, over here we have another discrete probability distribution that is very famous. In fact, it's called the coin tossing distribution. Do you know the other name of the distribution? Starts with B, Bernoulli distribution. The Bernoulli distribution is the coin tossing distribution. It's going to lead us to finally to a statistical loss for binary classification, and from now on we can be expanded to multi-class classification. And the nice thing about it is it can be plotted easily. In fact, what you see here is the Shannon entropy. When the log is with base 2, the entropy is given in bits, but when the log is natural, the entropy is given in a quantity called nuts. It doesn't really matter. Unit that we are measuring kind of entropy. What really matters is the shape. And since we have just two events, if we go back to that kind of formula and have either heads or tails in this bent coin experiment, right? We take a coin, we bend it, and then we toss it n times. And we can start counting, what is the heads that came out of it, and what are the number of times the tails came out of this experiment. And we divide the total number of events to obtain a probability, right? That's how we always estimate probabilities, by counting. So we have a summation. How many terms we have in the summation? 2 terms. One is heads, probability of heads times log 2 of 1 over probability of heads, plus probability of tails, log 2 of 1 over probability of tails. So let's write down these two. So the entropy H, capital H. Now, because the probability of heads, the probability of tails is 1 over 1 minus probability of heads, as you can see, as you can understand, everything on the right-hand side becomes suddenly probability of a function of probability of heads. So we go and plot the capital H as a function of probability of heads. That's what we do. So in fact, the formula is actually shown just below the curve. Minus, because we have converted the log of 1 over p to minus log p. And that summation that we all are familiar with by now. And here we plotted the x-axis probability of heads, the y-axis is entropy. The question for you is, why entropy is 0 when probability of heads is 0?
Because we are 100% confident it begins.
We live in a world full of tails. We've never seen a single head in our lives here. And someone comes to us and says, you know what, I have a piece of information. The next thing will happen is tails. Okay, how much money would you be willing to pay to acquire this event? And this is obviously 0. 100% possible. The same thing happens over here. We live in a world full of heads. And right here, there is a maximum. Why? Why the maximum is at 0.5? Because, yes?
That would the outcomes are equally probable.
Yeah, that is the point where we have the maximum possible uncertainty as to what comes next. Any slight deviation from this point to the left or to the right will increase the portion of the number of tails on the left, the portion of the number of heads to the right, all the way to 0. Are we following what's going on the binary entropy scenario here, the coin tossing distribution, and what it is really? So we'll see this formula again in binary classification, but one thing is certain. Now that we understand what entropy is, we are going to do following experiment. This is basically what we will close the discussion because half of you are asleep, and I'm also converging towards sort of situation where I cannot speak that much longer. So I will present to you the concept of likelihood, which will give us the tool which is needed for us to define the loss function. This function over here in the block diagram that we started the whole discussion on, this guy over here. We are going to use entropy and certain other considerations to define this guy. If we define this guy, we have solved the problem because I have plenty of probability distributions to plug in here. I can open a statistics book and I can go through, oh, this is a nice distribution, let me try it, let me try it, and then finally somebody can tell me if what I plugged in over here is good or not. Problem is solved. Okay. As you can understand, nobody is going to be opening any statistics book and done these trivial problems that we are facing here, right? Like p-model could be Gaussian, p-model could be Bernoulli, could be something else. Very soon, though, this p-model will be constructed from elementary functions called neurons. The equation behind the p-model will end up being a pretty gigantic neural network. Right now, we are just plugging in nice equations like a Gaussian, a Bernoulli, and so on. But very soon, this will stop happening. But if you don't go through this initial construction, and someone starts drawing a block diagram over here, says, "Oh, this diagram will give you a nice y hat," no one understands anything as to why. As I told you, we need to understand the why is happening. That's what we are trying to label. For those who are wondering, are we in the right course? Okay, so let's see. So this concept of maximum likelihood is really the workhorse of AI today. For all models, from the simple linear model we have seen already to a very gigantic LLM, are trained according to this criteria. If someone, the name of Bishop, who is really the godfather of Bayesian learning, made a statement a year ago, actually, in fact, suggesting that, Bayesian computers are really the most powerful computers we can build. However, they cannot scale the way that maximum likelihood computers can scale. So despite the fact that we are able to create better losses and better statistical time machines, we are not able to, for a fixed compute, it's better to scale more the maximum likelihood computer than to invest in a Bayesianity. So that's why most companies today are able to scale with they are using maximum likelihood for this reason. Because everyone is operating under the regime of constrained compute. If the constraint is eliminated, everyone will have been doing Bayesian computers. Okay, so let's see the concept of maximum likelihood. The objective function we will build by studying maximum likelihood will be connected to entropy. And both of them will lead to the cross entropy. That's the trajectory we will achieve. Fortunately, we're not able to finish the whole thing, but I hope you review at least whatever we discussed today, because if you don't, and you come up in the same state as it happened today, trust me, your midterm is going to be a bloodbath. I'm just going to sign it right here. Okay? So make sure you don't fall behind. Okay? Ask questions in Discord. Get hold of the TA. When is the TA office hours? When is the TA's office hours?
6 to 7 on Thursdays.
6 to 7 on Thursdays. Good, at least one person knows. Okay, get hold of them because they will also advise you what and how to study. Okay, maximum likelihood. I'm going to present the problem and solve it as best as can given the time constraints. Up to this moment in time, we were dealing with supervised learning, but to understand maximum likelihood, I'm going to drop temporarily the label. I'm going to present a problem that has no labels, has only X's, right? We are in this initial block called data generator, in other words, right? And we are giving you some X's on the real line. Giving you some X's on the real line. This is X1, X2, dot, 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 Xn. And we're lumping all these kind of X's together in this calligraphic or whatever, strange capital X. These are all small letters, right? Small letter X's. And I ask you a question. Give me a P model that fit the data. Well, come up with a probabilistic model that fit the data. I mean, is this a reasonable question? Yeah, since many of you must have grabbed some data at some point, and this data, you press the button in Excel, and a nice histogram came about that matched the data. Right? That's basically the simple exercise we are in. This comes also in the name of density estimation. Probably have heard about the problem of density estimation, and so on and so on. Okay. So the Vapnik said, you know, hypothesis. I need to come up with a hypothesis for this P model. Are the data real or discrete? They are real. They are continuous, random variables, right? So, what is a good Gaussian distribution? It is Gaussian, right? So, I am going to. I mean, everyone can assume anything. You can come up with a chi-squared, a beta distribution, any other continuous Fourier distribution is fine. So, I'm going to assume that my P model is X given W, as I call it over here, is normal with X given W is 1 over square root of 2 pi sigma squared X minus X minus mu squared divided by 2 sigma squared. Do you agree? Is this a univariate Gaussian model? Is this a hypothesis? Right now, there's no hypothesis. Because why there is no hypothesis? Because I haven't picked up the W's. Before, I was telling you, this is another line that I can assume, not another line. I have assumed certain values for W0 and W1, if you remember. What are the parameters here? What are the W vector here? What are the parameters of a univariate Gaussian? No one knows the parameters of a univariate Gaussian. Yes?
Mean and variance.
Mean and variance. Okay, thank you. Thank you. So this is basically W. This is my W. I am claiming that I'm offering to you a hypothesis that is the white hypothesis. Is this a valid hypothesis?
Yes.
Yes, absolutely. It is a valid hypothesis. Similar to the trajectory where we are doing before, we need a function for us to tell us if it is a good hypothesis or not, and an algorithm to move it if it is not. Okay? Similar steps. So the moment I have a hypothesis, I have an equation, and I have a specific parameters, etc., that I can select. I converted the equation to a parameter estimation problem. So the question became Q prime. What are the parameters of the P model that fit the data? The parameters do not fit the data, the hypothesis fits the data. Right? Did I face a parameter estimation problem before?
Yes.
Oh, that's good. So what did I do to solve it before?
In the direction opposite to the gradient.
I had to employ optimization theory to solve it, to come up with an optimal parameter. What every optimization algorithm needs to do anything. Every optimization problem can be posed as an objective function subject to constraints. That is what you have done many years ago, even though you don't remember. So we need an objective function. We have no constraints here, but we need an objective function. We need an objective function that will behave as follows. When the hypothesis is far away from the data, the value of the objective function will return a scalar, a positive scalar, which is small number. And when the hypothesis is very close to the data, or closer to the data, that scalar number should increase or decrease? Increase. So now I'm not really calling it a loss function. I'm calling it an objective because I want to give it a positive spin, right? I'm facing a maximization problem here, not a minimization problem. So the Q double dot states what is the objective function of the optimization problem that will give us good understanding. This is where we stop. Because if I start, then it will be a very messy situation. We cannot reconnect again. And you told me that the deadline for dropping the course is next week, right? Next Wednesday. Yeah, so hopefully I will see you again and we'll continue from here.